Welcome back, young physicists. Have you ever noticed how a stretched rubber band seems ready to fly, or how a wound-up spring wants to release itself? That's potential energy quietly waiting to act. In physics, we define potential energy as the energy possessed by a body due to its position or configuration. Whenever an object is raised above the ground, compressed, bent, or stretched, it gains energy that can be released later. That's why we say a wound spring or a lifted rock has potential energy. This form of energy is stored, not lost. It's ready to do work when conditions change. And we usually represent it by the symbol capital U, the universal sign of stored energy. Let's explore one major type of potential energy, gravitational potential energy. Imagine holding a ball above the ground. The higher you lift it, the more energy it stores. Why? Because gravity is ready to pull it back down. This energy comes from the force of gravity acting on the object's mass as it gains height. So when we raise an object, whether it's a book or a bucket, we're giving it gravitational potential energy, even if we don't see it immediately. It's the energy stored by position in a gravitational field. To understand gravitational potential energy, we start by considering the work done in lifting a body against gravity. When we lift an object, we apply a force over a vertical distance, and that's exactly how work is calculated. Work done, represented by W, is equal to force multiplied by displacement. Now, what is this force? It's the weight of the object, which is calculated as mass multiplied by gravitational acceleration, or m times g. The displacement in this case is the vertical height the object is lifted, denoted by h. So when we substitute these into the work formula, we get gravitational potential energy, U, equals m multiplied by g multiplied by h. This equation helps us quantify the energy stored in an object due to its height above the ground. Elastic potential energy is the energy stored in a body when its shape or configuration is altered by an external force. This typically happens when we compress, stretch, or twist an elastic object. You'll commonly notice elastic potential energy in everyday objects like stretched rubber bands, compressed springs, or a bow that's been drawn back with an arrow. As soon as the external force is removed, these objects try to return to their original shape. In doing so, the stored energy gets released, often in the form of motion or vibration. The amount of elastic potential energy depends on how much the object is deformed and on its elastic properties, such as stiffness and flexibility. This energy, like other forms of potential energy, is measured in joules and is considered a specific type of mechanical potential energy. Potential energy is all around us, powering both nature and technology in fascinating ways. For instance, a dam holds back water at a height, storing vast amounts of gravitational potential energy. When released, this energy is converted into electricity through turbines, a process used in hydroelectric power stations. In smaller devices, like a toy gun or a mousetrap, springs are used to store elastic potential energy, which gets released rapidly when triggered. Even a simple pendulum stores potential energy at the highest point in its swing. As it moves down, this energy is transformed into kinetic energy, maintaining the motion. Athletes unknowingly use this principle too. Before jumping or diving, their leg muscles store potential energy, which gets released in the explosive movement that follows. From machines to gadgets and even living systems, potential energy is essential. It plays a vital role in ensuring dynamic function and efficient energy transformation in the world around us. Let's try an example. Suppose a 10-kilogram object is raised to a height of 5 meters. To calculate the gravitational potential energy, we use U equals m into g into h. That's U equals 10 into 9.8 into 5, which equals 490 joules. So the object now has 490 joules of stored energy because of its height. This energy can be used to do work, like turning a wheel or powering a pulley system. Let's wrap up everything we've learned about potential energy. Potential energy is the energy stored in an object due to its position or deformation. It's not in motion yet, but it has the potential to do work. Gravitational potential energy depends on three key factors: the object's mass, the height at which it's placed, and the gravitational pull acting on it. It is given by the formula U equals m multiplied by g multiplied by h. Elastic potential energy, on the other hand, is stored when an object is stretched or compressed, like a spring, a rubber band, or a drawn bow. This type of stored energy plays a critical role in many systems around us, from mechanical springs and water dams to bows, engines, and even in biological systems. Understanding potential energy gives us a solid foundation to explore how energy transforms and moves in the real world, making it a key concept in science and engineering.